Thank you for coming to the best session you're going to have in the next 2 days. Welcome to RISC-V Summit. Bill will introduce himself. This is Bill McSpadden, not Alasdair. If you know Alasdair, we give him all credit for this, but even more credit goes to Bill for filling in on short notice. As I said, this is an important session, 20 minutes. You have 18 minutes. You know your role, Bill. Go ahead and take it away. Thank you very much, everybody. Here we go.
All right, glad you're here. We got 16 slides to go over in 20 minutes. We've got a lot to cover, and I'll try and do the best I can with the slides that Alasdair gave me to present. I chatted with him for an hour yesterday. He's recovering from an illness. Wished he could be here. I said, well, you could record it. And he said, no, I got a frog in my throat. So he was not clear. Hopefully I'll be clearer than he is. And I've got a bunch of handwritten notes here to go through with you. First thing I want to tell you about is Tech Golden Model is the working group. We meet Mondays at 7 o'clock Pacific time for an hour to talk about Golden Model issues. You're welcome to join. You don't have to be a member to attend that particular meeting. It's kind of like a software tools meeting. You can contact me at bill@riscv.org. That should be easy enough to remember. And you can get a hold of Alasdair at aa2019@cam.ac.uk. He is at Cambridge. All right. That's the important thing that you need to know about the continuing work on the Golden Model. There's lots of ongoing work. The things that we're going to talk about today are the things that Alasdair is working on, primarily about pushing some of the infrastructure issues that we have with SAIL and moving those things forward. But there's other work going on. Testing, adding new tests to test the model is one thing that's going on. There's work that's being done to turn the floating point into native SAIL code so that we can have native SAIL code for the floating point operations. Currently, we use a C library to do that. All right, one other thing I want to reference is that Tim Hutt gave a really, really good talk yesterday. We've got to get that published somewhere and out there. He did a recording. By the way, you're lucky to have me up here. Of the two people who were doing SAIL presentations, both of them came down sick. And I thought I might end up sick because of that, but no, I'm here. Tim's talk was really good, and it dovetails nicely with this particular talk that we're gonna go through. Okay, what is SAIL? It's a domain-specific language, and it's meant to specify clearly and cleanly what the ISA is. It tells you what the instructions are, it tells you what CSRs are, and gives you a way of writing a good formal definition of what the instructions do. The upshot is that once these things are put in place, you can have a model that will now execute those instructions as intended. And they're meant to map directly to what the text in the spec says. It comes from the background from it, ASL, ARM specification language, sometimes called architectural specific language. It's an evolutionary growth of ASL. The benefits of SAIL, you've got strong static type checking. And this is both a blessing and a curse. It's a blessing in that it's unambiguous on your types. The curse is that you've got to get the code right. Okay, so it's the difference between having strongly typed and weakly typed languages. It has a really good exhaustive pattern matching scheme, and it's open source. From SAIL, you can get a number of different outputs that are useful. The ISS is the instruction set simulator. There's some tools in place to do symbolic execution with our weak memory model. So you can do some exhaustive testing with the memory model that we're using. We generate documentation. There are tools that allow you to take SAIL code out into ASCII form and can be embedded into specification, which we're pushing really hard. We want SAIL code to be in the documentation as the canonical reference for instructions. There's an effort ongoing for system Verilog hardware verification. Take the SAIL code, turn it into system Verilog that can then be used for all the formal tools, Jasper, for example, to do some analysis of that. And various theorem provers are also available that can be used. All right, on to the next one. This is a simple example of what some sail code looks like. Tim gave a real good example yesterday in his slide deck, and I encourage you to look at that. It's a bit different than this, and it's going to point out some things. I'll mention them here in just a second. This, in RISC-V, you have a type of instruction called an I type, an immediate type. I believe that's what the I stands for. And in this particular case, in one clause, we can talk about what the mapping is, the encode-decode mapping clause. We have the execute clause here as well. There's also an assembly language clause that goes with it as well, so you can do a mapping for assembly language decode. And in one nice, tight, compact bit of code, you know how these instructions are going to work. Okay, so for the @I, it's pretty straightforward. Take the source operand with the immediate, and you get the result. Notice that you have the, where's the match? You have the match op here. It says which operation are you going to run on. So this is the nice exhaustive mapping function or mapping capability that we have. This doesn't push the capabilities of that so much, but it gives you the idea of how you would specify an instruction. And this maps almost identically to what was in the text spec, and that was the way it was intended. Read the text spec and implement, write your code for it, and it comes out very nicely like this. We have the simple case of a retire success. Now, this is the pathologically simple case, right? These are real simple. The hard ones, if you go and look at the load store instructions, that's where things get messy. But they're messy for every architecture, okay? It's not just RISC-V, but think of all the things that have to go into the load and store. The address translation, you got your PMPs, PMAs, virtual memory, all that kind of stuff has to be evaluated. Has to be evaluated based on privilege. All of those things have to be evaluated. And the code's fairly lengthy, but it is explicitly spelled out what has to happen. Let's see, what else to say about this one? In Tim's example yesterday, he gave a really good example of the strong type checking that goes on for one of the examples that he gave. He says this emphasizes the value of SAIL and its strong type checking, and I would steer you to his talk about that. All right, on to the next. Where are we at today with regard to the SAIL RISC-V? The core ISA is in place for RV32 and RV64. We have vector support that's in place. Many of the Z extensions are in place. There's a few key extensions for the RVA23 profile. We're missing hypervisor, and that's a tough one that's being worked on right now. We have someone who's working on this. But it turns out the hypervisor touches all sorts of different parts of the model, as you might imagine. So it's being worked on, and it's a more difficult extension to implement in SAIL than, say, like vector. Vector's big, but it's just one feature that gets added onto the side, and it can be taken in and out fairly easily. Hypervisor's not that way. Configuration. Most of this talk today, a lot of this talk today is going to be talking about configuring the model. This has been a bugaboo for the SAIL model ever since I started working on it, is that there's not a nice way to configure it, and we've been working on coming up with a better solution for configuring it, and Alasdair has taken on that task. We intend to have a good configuration story and a merge to the master, the main branch, giving us a solution to the runtime configuration capability. We're going to talk about that here in the next few slides. But before we do that, we'll talk about some other uses of SAIL. It's being used as a design tool for Cherry RISC-V and Chariot. Both are extensions to RISC-V, and it's being actively used. It's also been used in several other architectures as well. So it's not just RISC-V. We have a good usage good user base for SAIL. The vision when SAIL first got put out there was that this would be a model for the primary design tool for specifying the architecture. And the goal stated originally is we want the SAIL code to be used as the documentation for all the instructions. He makes the statement in here, for our own projects, we develop the SAIL model and document it as a single integrated artifact. There are projects, or the Cambridge projects that they're working on. So it's not just RISC-V, it's some of the other projects. And what we want is we want to see the SAIL code in the spec so that as you read the specs, you naturally learn what the SAIL language is. SAIL language is not tough, okay? Sometimes it's looked at as being rather exotic and whatnot. It's not. It's the way that you would specify an ISA. Now that may be a little different for some people for thinking about how you might canonically write an ISA, but it's not that tough. It's the type checker that makes things a bit difficult. The other thing that you get is open source tooling. All of the tools that we use for SAIL and the development of the SAIL model are open source. All right. We're working towards full RVA 23 support. The big portion of that is getting hypervisor and getting the configuration in. So that's being worked on by volunteers. I'm the only one paid to do this work. I am actually an employee of RISC-V International, and I spend a good portion of my time not doing coding, but doing project management stuff. We need volunteers. We need able and willing volunteers to contribute to the SAIL model. We've got new specifications. You guys sit in the meetings. You've seen the specifications as they're coming down the turnpike. A lot of them coming along, and we need more people contributing to it. However, saying that, our bottleneck today is not the implementation of extensions. Our bottleneck is in PR reviews. We need more people who can sit down, read a PR, and say, bless it or curse it, so that we know how to propagate the PR. And currently, we have a big backlog of PR reviews. We've got about 18 active contributors right now. Some of them are sitting here, and I'm staring at one right now, who are actually contributing to the model. One other thing that Alasdair wanted me to mention is that he's working on a language server for VS Code so that we have a better IDE experience for SAIL. All right, documentation. There's an ASCII Doctor plugin that we can do, that we can add into our documentation for our specs. Where the backlog is on this, we need SMEs, subject matter experts that know how to take SAIL code, see what the SAIL code is, and figure out where it goes into the spec. Sometimes it's straightforward, sometimes it's not. But what we're missing is the subject matter experts, the spec keepers that can hop in and add that to the documentation. One of the struggles that Alasdair has is that we have two GitHub repositories that are being used. There's the SAIL GitHub repository and the spec GitHub repository, and they're not the same. And so how do you keep those two in sync? So that's a question that he's wrestling with to try and figure out what the best way of dealing with that is. Any ideas or feedback, he wants to hear them. So do I, but he's the one who's asking for it. Here's some documentation examples, what you would get. You get a nice little diagram of what the instruction looks like, plus the operation. You can, and by the way, on this add I case for itype, if you remember, there was the match clause, right? Well, what he did was he said, well, I just want the add I portion of it so that I can put that in. And this is the method that you're able to do, is say, I want the add I, plug it in here. This goes on, by the way, this was presented at last year's summit, and work has progressed on that. Configurability. Let's see, I've got 4 minutes left. We need runtime configurability. For the longest time, the SAIL model has been looked at as, well, if you're going to add a feature, just recompile it and do the model and execute that model. Recompilation of the model is not good for our customers. We want a model that does not need to be recompiled every time you want to add a new feature. So we need runtime support in the model. And that's been something that we've been working on really hard to get right. And Alasdair, I put a proposal out there 2.5 years ago saying, let's do it this way. And Alasdair said, no, we really need some language support in Sail to support this. Our goal is to have runtime configurability, a good story, and something on the master branch by the end of this year. Okay, and he's actively working on it. He's got a proof of concept that demonstrates what his ideas are, and that's where we're at. So think along the lines of a whorl field that has a varying width. Okay, how do you dynamically do that in a strongly typed system? That's why the language has to have some support in it. All right, so that's the schedule. Configurability also, on this next one. There are times where you want the static build capability so that Sail gives you the full type checking capability. And the tool that's being worked on converting Sail into system Verilog as a system Verilog model, you want to have everything explicitly called out on widths and whatnot. So there is a capability of having constructs that reference key value pairs. Right now he's implementing it with a JSON file to get the key value pairs to do configuration. Another configurability capability, this has to do with, no, this is not the module system, is it? Yeah, it is, they're middle bullet. He's implemented a module capability so that you can say, I want this, but not that. Currently, today, the make file is the thing that tells you. You give the make file an option and say, I want to make this particular thing. And it's messy, and it's ugly. Module capability allows better checking, better readability, better maintenance. So there is a module system that's in place. Think of the two examples I gave earlier. Vector is a standalone block off to the side, and the module capability would say, no, we don't want the vector. We'll just take everything else and leave vector out. Okay? So you can swap it in and out. The bigger problem is hypervisor, where hypervisor's fingers span all the CSRs and a lot of the instructions. How do you specify that in a module-based capability? He wants your input on that as he works through it. Let's see, I've got a minute left here. Make another mention about one of the, in my estimation, when it comes to the architecture, one of the critical things that is needed. The ISA and the CSRs and how all those work, we understand how to do that, all right? That's not particularly difficult. But when you get into a system, a multi-heart, multi-core system, how do you guarantee memory ordering effects? We have a weak memory ordering model. How do we prove, how can we check to make sure that our ordering rules work correctly in an implementation or in this particular model? There are tools that are available to do WMO support. Throw in a whole bunch of memory accesses using load reserve store conditionals, using any of the atomic operations, memory operations. How do those things work, and how can we guarantee that the ordering all works correctly? How can we prove that? There's tools that Alasdair and others have used to guarantee that that's the case. His comment to me yesterday was, we found some really good bugs on memory ordering issues that we had. I can't remember what the project was that he was working on it, but that was an important feature. All right, I'm being told to stop because we're out of time. Thank you for being here. Thanks for being courteous and not throwing tomatoes at me. Again, get a hold of Alasdair or I to talk about the Sail model. Thanks much.
All right, let's give him a big hand.